Hello everyone and welcome to the first lecture about machine learning. And now we are going to learn an overview of machine learning. So over the next few minutes, we will not just define machine learning, but we will explore its origin, its necessary foundation, and also its critical role in modern world. Let's begin by defining the umbrella term AI. The commonly accepted and highly practical definition for AI is that it is a study of how to make computers to do those things at which, at this moment, a human being is doing it better. This is not just about making a computer think. It's about engineering solutions for complex, real-world problems that traditionally require human cognitive abilities. Think of tasks like understanding human language, recognizing faces, or navigating unstructured environments. The field of AI seeks to bridge this performance gap, constantly pushing the boundaries of what machine can achieve. So, machine learning is the primary engine driving this progress today. We want to build models of ourselves. So, here we have the terminology of machine learning. And machine learning is only one branch of AI. So what is machine here? Machine is any device which has computational capacity to process data and execute algorithms. What is learning? Learning is the adaptive process that results in measurable and continuous improvement in the machine's ability to perform a specific task based on experience or data. So together, this machine learning is the field of study dedicated to programming a computationally capable machine to achieve improvement in performance on a task. How? By autonomously deriving knowledge from data rather than following explicit instructions. So machine learning is a branch of AI. We already learned that AI has four different branches. The first one is problem solving by search. The next one is knowledge, reasoning, and planning. Third one is learning, that is machine learning. And fourth one is communication, perceiving, and acting. Right? So machine learning is the third one. In machine learning, we have four different categories. So machine learning itself is broken into various paradigms, which we will touch on later in the use cases. So the first one is supervised learning. This is learning from a data set where every example is labeled with the correct answer. The system is supervised by the ground truth. Then we have unsupervised learning. This involves analyzing unlabeled data to find hidden patterns and intrinsic structures. The next one is reinforcement learning. This is how systems learn to make decisions by performing action in an environment and receiving rewards or penalties. There is no data in here. Then we have semi-supervised learning. Semi-supervised learning is something between supervised learning and unsupervised learning. This is a kind of hybrid approach, and this leverages large amount of unlabeled data alongside a smaller amount of labeled data. Then on top of them, we have deep learning. This is a subfield of machine learning that uses deep artificial neural networks, network with multiple layers, and we use this one to analyze complex data patterns. So we may have deep supervised learning algorithm like deep neural networks, or we can have deep reinforcement learning models. The significance of machine learning is best underscored by the leaders who shaped the industry. This is not hype, it's a fundamental economic and technological shift. Bill Gates, the chairman of Microsoft, put a monetary value on it, claiming that a breakthrough in machine learning will be worth 10 Microsoft. Tony Tether, the director of DARPA, compared its disruptive nature to the internet itself, and by calling machine learning is the next internet. And even the core functionality of major search engine is driven by machine learning, as Prabhakar of Yahoo highlighted that web ranking today are mostly a matter of machine learning. These quotes that you can see here from different industry leaders cement the idea that machine learning is not just an academic curiosity, but the defining technological discontinuity of our time. We utilize machine learning because it allows us to tackle problems that are either too large, too complex, or too subtle for traditional rule-based programming. Consider autonomous driving. For autonomous vehicles, writing rules for every possible route condition, pedestrian action, and weather event is impossible. Instead, machine learning systems learn to drive by observing millions of real-world scenarios. In medicine, machine learning is revolutionizing diagnostics. This machine learning can detect up to 50 eye diseases by analyzing retinal scans with greater speed and consistency than human eyes, and this freeing up specialists for more complex cases. And in our personal devices, facial recognition is powered by complex algorithms that learn the unique, subtle patterns of your face from numerous images, and in this way, they allow the machine to unlock your phone with high security and speed. Machine learning is the engine, but data is fuel. This illustration that you can see here, data, information, knowledge, insight, wisdom, and impact, this beautifully captures the progression of data value. We start with data. Data are just disconnected points, or you can say raw stuff of the world. You can say anything that we can save on a computer is data, like figures, images, data, text, books, audio, everything, right? As we apply structure and context, they become information. So you can say information is structured data. When we connect the information through rules and patterns, it becomes knowledge. Knowledge is actionable information. Machine learning excels at taking knowledge and turning it into insight. How? By identifying the most critical connections, which through application and experience evolves into wisdom and ultimately creates measurable impact. So the greatest power of machine learning lies in accelerating the journey from raw data to actionable insight. Machine learning is the science of making computers learn and act like humans. How? By feeding data and information or experience without being explicitly programmed. The paradigm shift is evident in the process flow that you can see here. So a traditional system is giving explicit instructions. However, a machine learning system takes data or label, or you can say experience, and through an iterative process, they try to learn. What to learn? They learn a program or they learn a function or a model, right? Then they use this learn function or model to what? To do prediction on new data, unseen data. Crucially, the system can then evaluate the prediction and they try to improve their performance over time, embodying the concept of what? Learning. So learning, it means improvement in performance. So there are several important steps in development of machine learning model. The first one is objective definition. First of all, we need to know exactly what we want, right? Based on our objective, we try to go for data collection. We try to collect all relevant data from various sources. Then we go for data preparation, like data wrangling, cleaning, and converting raw data into a format that allows convenient consumption. Then we go for data analyzing, like selecting and filtering the data that's required to prepare the model. Then we go for algorithm selection because we have too many algorithms in machine learning. Based on our objective and data that we have, we must select an appropriate algorithm. Once we have selected an appropriate algorithm, we go for algorithm training. In here, we train the algorithm on the training data set through which the algorithm understands the patterns and the rules which govern the data. Then, once we have trained our model, we need to test our model. We need to determine the accuracy of our model, and we try to do prediction. If it's okay, then we go for deployment by deploying the model if the speed and accuracy of model are acceptable. Jumping from zero to machine learning is not recommended at all. Machine learning needs some prerequisites. So a strong Python programming skill for implementation of machine learning model is mandatory. Solid understanding of data structure and algorithm is very important. Calculus and discrete mathematics are essential for understanding optimization and parameter updates. Statistics and probability, they provide a theoretical framework for inference and probability. As I said, calculus and its concept like derivatives are necessary for parameter optimization and loss function, often through methods like gradient descent. And statistics and probability, they underpin sampling, reasoning, and quantifying uncertainty in prediction. Linear algebra is very important as a part of algebra family. It is critical for efficiently representing and manipulating high-dimensional data and performing large-scale matrix operations. And then you can say, for example, information theory is very important because it helps in quantifying the surprise or uncertainty in data, and it is the basis for measuring information gain and errors. And also, real analysis, numerical, computational, basic geometry, for like basic formulas, functions, exponential, logarithms, Euclidean distance. Distances are very important, like in clustering, they are very important. Operational research. So if you aspire to move beyond using a pre-built libraries to becoming an architect of new algorithms, these mathematical disciplines are non-negotiable. So there are too many use cases for machine learning like classification, regression, anomaly detection, clustering, and many others. Machine learning models are typically defined by the type of the problem that they solve. For example, classification, if you want to predict a category. So this is the task of predicting a discrete category, right? It means something belongs or do not belong to a category. So you can see here, for example, in this image that you can see here. So for example, we have some data, and based on some feature, we can decide, okay, that this image that we have, they belongs to cat or dog, right? So two classes. This is cat class and this is dog class, right? Based on what? Based on features. The next one is a regression. A regression is for continuous quantity. For example, instead of classifying a person as old or young, we are predicting the precise age based on factors like height and health. Or you can say, for example, you want to predict a price of a house based on different characters, right? Or age, right? So we go for continuous. So in classification, we go for discrete output, as I say, 0 or 1, or even multi-class classification. For example, when a Tesla car is driving in a street, there are too many objects that they need to classify. For example, cars, buses, bicycles, motorcycle, pedestrian, stationary object, road obstacle, and many other things, right? So these are called as classification. However, if the output is continuous, for example, price, right? So price can be from $1,000 to $10,000, right? So this is continuous. Or age. right, or height, or so these are continuous. The next one is anomaly detection. This aims to detect an anomaly, a point or event that is statistically rare and deviates significantly from the expected pattern, right? For example, you can see here, these data are out of the range of this rest of data that we have. So a primary application is detecting money withdrawal anomalies. You can say, you can call them as a fraud detection. And how? By observing patterns that do not fit a user normal behavior. The banks, they try to monitor your expenses, and if suddenly some big amount has been withdrawn from your account, they can detect it as anomaly, right? Because it is out of the normal. Or even, for spam detection, right? They try to, study the behavior of your emails, and if suddenly some email came out of your scope, then they consider it as spam. Or the next one is clustering, right? So in here, in classification, we have labels. It means before we go for classification, we know how many kind of classes we have. But in clustering, we don't know how many data we have. We call them as unlabeled data. So in clustering, it's a kind of form of unsupervised learning. So the first one is supervised learning. This is a supervised learning. This is a supervised learning. Anomaly detection also can be supervised learning, but this is unsupervised learning, and we use to discover structure in unexplored data. The goal here is to group similar data points together. For example, a business application is finding group of customers with similar behavior to create effective marketing segment. Or for example, social media, they try to suggest your friends, right? How? Based on your similarities. Clustering. To put it simply, machine learning is a solution to the problem of software complexity. As systems become vast and the requirements constantly change, writing software is the bottleneck. So machine learning is automating automation. It is literally getting computers to program themselves. Instead of hard coding every rule, we let the data do the work instead. This adaptability is what makes machine learning so powerful. People often think of machine learning as a magic, but it's grounded in process. A better analogy is gardening. The algorithms are like seeds. You choose the right seed, for example, a neural network or decision tree for the soil. The data is like nutrients, right? High quality, clean, and abundant data is essential for healthy growth. You are the gardener. You are responsible for preparing the ground, watering, and pruning. Then the resulting program, you can say the learned models or function or anything you can call them, they are plans. Your program's success depends on the quality of your input like data and the suitability of your method like algorithms. The machine learning framework is the technical blueprint for the learning process. The fundamental objective here is to learn a prediction function or model, you can say f, in such a way that the output y is a function of the input x, or you can say mathematically y is equal to f of x. We must first convert it into a feature representation, a numerical vector that the computer can process. Then we apply the learn prediction function like f to these features to get the desired output, for example, apple. So the learning process is the function f that is estimated during the training. Then we use a training set of label example, like for example, x1, y1, up x2, y2, up to xn and yn. And the goal is to minimize the prediction error of this set. Then we go for validation and testing. In here, we try to avoid overfitting because we use a separate validation set to tune the model's hyperparameters, and we try to optimize its generalizability. Finally, the true measure of success is testing. We apply the final, it means frozen learn function, to a never before seen, right? It means once we train on some apples, then we try to test our model with a new image of apple, not those in the training set. We call never before seen, and we add it like x, then we see how is the output, right? So if we give x, we expect to get this label, right? This is the label. So we show the image of apple, and the model should be able to map this one to word of apple. If we show tomato, tomato. If we show cow, cow, right? This is for image recognition. So the output like cow, tomato, and apple is y, and this is the prediction function or the model that we have trained, and this is the image feature that we give it, right? So we will give them, and we will wait for the prediction. So here you can see the flow, how it works. We have a training data, so we have like 10,000 images. So we have apple, pear, tomato, cow, cat, and horse. So these are the images. We call them as training images, right? These training images are given to the model, and the model try to extract the features like shapes of these different images. Then in the training process, they try to assign label to each, right? So this is apple, this is pear, this is tomato, cow. So different, they will be added, right? And in an iterative way, they try to minimize the error. Error is the difference between predicted and actual. So maybe by mistake, the model recognize this one as apple, applet, right? This is an error. So in the next iteration, the model try to learn and improve the accuracy. Finally, after too many iteration and training process, we have a learn model. That is the function, right? Then in the next step, we go for testing. So this image is not in this data set, right? So we call this one as training data set. And this one is testing data set, right? This is a new image. It's not here already. We give it to the model. The model try to do feature extraction and do prediction. If the prediction show this one as an applet, it's okay, right? Otherwise, the model doesn't work well. So we have a fundamental shift in software development paradigm from traditional programming to machine learning. In traditional programming, the input was data and program. Then we have some output, right? But in here, in machine learning, we have data and output. Then we try to build a model, right? Or program, or you can say function, right? So we have input and output. We give it to computer. Computers try to learn and build a model. So in traditional programming, you are the expert writing the instructions. However, in case of machine learning, the computer is tasked with becoming the expert, analyzing the data and answer to discover the hidden instructions. Despite the diversity of algorithms, tens of thousands with hundreds new every year, every single machine learning algorithm has just three essential components: representation, evaluation, and optimization. Representation answers what is the hypothesis space, or you can say what is the models for. The representation defines the set of functions the learner can possibly learn. Examples include structured representation like decision tree, or complex continuous model like neural networks or support vector machine, and many others. Then we have evaluation. Evaluation answers the question of how good is a given hypothesis or model. This is quantified by a score function, like for example, you can say loss function, cost function, or you can say a performance metric. For classification, this might be accuracy or precision and recall. For regression, it can be square root and the rest that you can see here. It means we want to see how good is our model performing. And next one is optimization. Optimization is used to answer the question of how do we find the best hypothesis. In here, the goal is to maximize the evaluation score. This involves searching the hypothesis space. Techniques range from combinatorial optimization, like for example greedy search, to calculus-based approach like convex optimization using gradient descent, which effectively finds the lowest point on the error surface. Or we can go for linear programming. Machine learning sits at a unique crossroads. While it is primarily focused on the accuracy and effectiveness of the computer system, it draws immense strength from various domains. Machine learning shares its rigorous methods of inference and modeling with statistics. It benefits from the infrastructure and techniques of databases and information theory, and it intersects with control theory when designing systems that interact with and modify their environment, like robotics. Also, data mining, decision theory, cognitive science, psychological model, neuroscience, evolutionary models. Machine learning has interacted with different fields. We utilize machine learning because it provides a mechanism for programming computers to optimize a performance criterion, how using example or experience. Learning is not always necessary. You don't need machine learning to calculate a payroll. Learning is essential when human expertise do not exist. For instance, in designing navigation system for extraterrestrial exploration like Mars, or humans are enabled to explain their expertise. We know how to speak, but formulating an explicit set of rules for general speech recognition is virtually impossible. Or the solution needs to be adapted to particular cases, such as customizing a user interface or biometric authentication to an individual. Fundamentally, we aim to build a model that is a good and useful approximation to the data, moving from cheap raw data to expensive and scarce knowledge. One key application is learning association. The most famous example is market basket analysis. The goal here is to find relationship between variables. How? By calculating the conditional probability. For example, probability of Py given X. This is the probability that someone who buys item X will also buy item Y. The system learns the likelihood of buying chips given that a customer has already bought a beer. So if we just try to follow this probability, it's not machine learning. But if we have a set of data set, a large data set, and the model try to learn or extract this probability based on this data set, then it is machine learning. And let's revisit classification with a detailed example like credit scoring. The task is to distinguish between low risk and high risk customers. So, for example, a bank, they have too many customers and they want to determine whether they are low risk or high risk. Low risk, it means they will pay their expenses at the end of the month that they use via credit card. High risk, it means they will not be able to pay, right? And based on this one, they can adjust the credit card limit, right? So, for example, some people, they can buy $10,000 every month via their credit card, and some people, they can buy only 500, right? So these are low risk and these are high risk. So Based on what? Based on the data set. Then we try to extract the pattern, right? So if income is greater than some desired amount and saving is greater than like theta 2 as another amount, then this is a low risk. So we can give them $10,000 credit per month. Otherwise, we should give them 500 only. To consolidate our understanding, let's look at machine learning at a glance. Machine learning is the study of algorithms that improve their performance at some task with experience. This is accomplished by what? By optimization, by optimizing a performance criterion using example data or experience. Statistics provide the vital role of inference from a sample, and computer science provides the framework for efficient algorithms that they are necessary to solve the optimization problems and also for representing and evaluating the model for inference. The commercial imperative for machine learning is threefold. So the first one is data abundance, the second one is computational power, and the third one is competitive edge. So in the case of data, lots of data is being collected and warehoused from sources like, for example, e-commerce data, web traffic, credit card and transaction, and the rest. This raw material makes machine learning feasible. Then we go for computational power. Computers have become cheaper and more powerful. So in this way, they can provide the necessary speed and capacity to run complex algorithms on huge data sets. And the next one is competitive edge. Competitive pressure is strong. Companies must provide better customized services such as personalized recommendation in customer relationship management to gain an advantage. Machine learning is the tool that makes this customization scalable. Beyond commerce, science is pushing the limits of machine learning. Modern scientific instruments generate data at phenomenal rates, sometimes gigabytes per hour from telescopes, remote sensors, and gene expression microarrays. Traditional techniques are infeasible for raw data at this scale. So machine learning may help scientists by efficiently classifying and segmenting data. It can also assist in hypothesis formation by identifying subtle correlation that a human might miss. For example, the famous image from the black hole required a massive coordinated machine learning effort to stitch together and process petabytes of raw data. To conclude, machine learning is no longer confined to research labs. Machine learning is integrated into the fabric of our digital lives through essential applications like spam detection. In this way, they protect our inboxes, credit card fraud detection, secure our finance, speech recognition powers virtual assistants, face recognition for our mobile phones, and many other things, product recommendation that fuels e-commerce platforms and sentiment analysis, and many more. These systems work tirelessly and automatically. They demonstrate the profound practical impact of machine learning. Okay, thank you once again for your time and attention. I hope this detailed overview has provided a clear picture of machine learning field. I am now open to any question, comments, or concern you may have. Please feel free to reach out me via the email that provided here. Thank you and see you in the next lecture.